With systems of equations, what we're going to have is multiple equations working together. And to solve them, we're looking for a coordinate where they all line up with each other. So that coordinate would be a solution for all of the equations. So for this first example, what we're going to do is just check whether or not a coordinate is a solution to the system. So in this first case, our system of equations is that x plus y is equal to 7 and x minus y is equal to 1. So what we're looking for is a coordinate that satisfies both of those equations. So what we would do is plug in. So we have x plus y should equal 7, and then we should also have x minus y equals 1. So what we're going to do is plug in 4 for x and 3 for y. Now with this first equation, 4 plus 3 is in fact 7, so that works. But to make it a true solution to the system of equation, it has to work for the other one too. So 4 minus 3 is 1, which is in fact equal to 1. So yes, 4, 3 is a solution to the system of equations, because it worked for both. As soon as it fails for one, it fails for the whole system. Let's try this out with a more complicated system of equations. So we have this 2x plus 3y equals -5 and 7x minus 3y equals 26. And what we're going to do is plug in x equals 2 and y equals -3 and see if it works. So 2 times x plus 3 times y is equal to -5, and we're going to plug in 2 for x and -3 for y, and we'll solve. So 4 minus 9 equal to -5. Yep, that one works out. So we've got one solution. Now we try it for the other, where we have 7 times x minus 3 times y equals 26. And we're plugging in x equals 2, y equals -3. So we have 14 plus 9, and that's going to be a 23, which does not equal 26. So while 2, -3 is a solution to one of the equations, 2, -3 is not a solution to the system of equations, because it failed one of them. Okay, so we're looking for this coordinate that works for both equations. And what that means in terms of graphing is if we graph the two linear equations, we're looking for the intersection point. That intersection point is our solution. So with these three problems here, what we're going to do is get lots of practice with graphing our linear equations. Just we're going to be graphing two linear equations at the same time. So for this first scenario, it is very nicely in y equals mx plus b form, our slope-intercept form. So I'm going to graph y equals 2x minus 4, and I'm going to graph y equals x minus 3. So graphing y equals 2x minus 4, what I'm seeing is a y-intercept at -4. I'm also seeing a slope of +2, which means we're going up 2, right 1. So let's graph that point. Oh, first let's label our axes. So we have x and y axes. Let's go ahead and use increments of 1. And we're at 0, -4 with a slope of 2. 1, 2, 3, 4. And a slope of 2 to get some coordinates going. And there's our first line. All right. There we go. And now we'll do our second line, which has a y-intercept at -3 and a slope of +1, which means we're going to be going up 1, right 1 to map to our points. So 0, -3. Oh boy, We're real close there. Maybe I should have spaced these out, but we'll be fine. And then up 1, right 1. So there we can see our intersection point, but let's go ahead and get these graphs going. All right, here we go. And as you're graphing by hand, just be really careful and use a ruler or straight edge to be as exact as possible, because we really want to see where that intersection point is. So what we have there is an intersection point at 1, -2. And that intersection point is our solution. And what we need to do is when we're graphing, and even when we're solving with our next ones, a common mistake is to just kind of finish here. But you need to state what the solution is. It's kind of implied here, but what we would want is some sort of statement like the solution is 1, -2. And then what we could also do, and that would be our final answer, maybe before we make it our final answer, it would be a good idea to check that that in fact works. So plugging in, like we should have y equals -2 when x is equal to 1. So at 2 minus 4, yep, that's a -2. And then plugging in for the other equation, 1 minus 3 is in fact -2. So that's just a kind of a quick little mental check there that it all works out. All right, so what if it's not nicely in y equals mx plus b form? Well, we can put it into y equals mx plus b form. So if we have x minus y equals 4, also you could use, in fact, let's do that. Just for some more practice from our last videos, let's use x and y intercepts here. So x minus y equals 4. And let's start with the y-intercept. So that's when we plug in x equals 0, which is a -y equals 4, which gives us y equals -4. So we have 0, -4, and x-intercept, we're going to plug in 0 for y, so x minus 0 is equal to 4, so x is equal to 4, so we also have the coordinate 4, 0. All right, so let's use increments of 1, x and y axes. So it's 0, -4, and 4, 0. And what we're seeing there is a nice slope of 1, so we could get some extra points if we wanted to plot, but that all looks good to me. Okay, connect the dots, and we have our first line. Let's go ahead and do this with our second line. So x plus y is equal to 3. And let's start with our y-intercept. So plugging in x equals 0. So y is 3. So we have the coordinate 0, +3. And then for the x-intercept, we're going to have x plus 0 equals 3. So x is 3. So we have 3, 0. So 0, 3, 3, 0. Ooh, and this is going to get interesting. So you have a nice slope of -1 there. And let's connect those dots. And this is where being very careful and accurate is so important, because we're actually landing in the middle here. And let's go ahead and call this 3.5 and -1/2. And what we can do is double check our answers to make sure that that is in fact what's happening. So let's check our answers before we use that as our final conclusion. So 3.5 and -1/2. Let's plug it in and see what happens. So x plus y equals 3. So 3 plus 5 plus a -1/2 equals 3. Yup. And then x minus y, -1/2 is equal to 4, which is 3.5 plus 0.5. Yep. Okay, so that is in fact our solution. So we need to make our statement. So the solution is 3.5, -1/2. All right, and that would be our final answer. We even checked it and it works out perfectly. So I like this example too because it does show not a flaw, but some issues that come up with graphing and why we have to be so accurate. But imagine if these were messy fractions, like thirds or sixths or anything like that. That would be very, very difficult to visualize here. So that's where in the next videos we're going to look at solving algebraically, because that'll get us to the exact solution. So while we'll do some of these graphically, we will really move to algebraically so that we can get those exact answers in those messy solutions when it might be difficult to see visually whether or not it's coming out to like a perfect whole number, or like in this case it was nice halves, but when the fractions get messy, this gets harder to do. All right, one more case here. Okay, let's with this one do changing it to y = mx plus b form. Which for this first case, all I need to do is divide both sides by 2, which remember we have to divide absolutely everything by 2. So I'll give us y equals 4 divided by 2 is 2, and then minus 2 divided by 2, which is 1. So we have a slope of 2, which means we'll be going up 2, right 1, mapping to our points, and then we have the coordinate 0, -1. All right, so let's go ahead and graph that. Let's use increments there, and 0, -1 with the slope of 2. Okay. And let's go ahead and connect those dots. All right. Then let's get our other line. So we're going to have 2x minus y equals -1. Let's go ahead and subtract 2x from both sides. And then we're just going to need to multiply everything by -1 so that y is positive. So that's just going to change the sign of everything. So we'll have positive y equals positive 2x plus 1. So we're going to have a slope of 2 and y-intercept of 0, +1. All right, 0, 1, slope of 2. And what we're going to have here, oops, too close. There we go. What we're going to end up with here are parallel lines, which, as we talked about before, parallel lines never intersect with each other, which our whole thing here is looking for intersections to find a solution. So if they don't intersect, then there's no solution. So what we end up with here is just an answer of no solution. There's no coordinate that works for both of those, for that system of equations. Because they're parallel, they'll never intersect with each other. The other special case that can come up is if you're graphing and you end up graphing on top of the same line. In those cases, it would be infinitely many solutions. And in fact, the solutions come from the equation of the line. So that's our other special case, is when you go to graph, it ends up actually graphing the same line. But when you end up with parallel lines, that's a case of no solution.